Michael today, you're talking about how to obtain any result you want from discrete choice model.
Yep. And now you see how it happens, and but
is this a post-truth kind of seminar?
No, this is a pre-truth seminar. So the problem, boldly stated, lots of papers out there that are publishing results that would change if the analyst had made what is essentially sort of an innocent, an arbitrary change that you wouldn't really think of as being an issue, and it would fundamentally change the results you're presenting. So that's my bold claim, and that no one recognizes that when it happens. In order to get to that, we need two sort of building blocks, and some of this people will know, but I just want to make sure that everybody's on the same page. So we're going to be interested in these things called random parameters. So just assume that you've got some function you're trying to estimate, v, so that could be an observable variable, or it could actually be a latent variable like utility in a choice experiment. And it's a function of these three variables, f, f1, f2, f3, and the standard process is we're going to estimate the parameters beta1, beta2, beta3. There's some sort of measure of the weight, the margin utility, or the value associated with those variables. And starting point usually is that those are constant, as in they're constant across the sample. If you want to extend that, you have this idea of, well, we're going to have some personal individual heterogeneity. So instead of having fixed coefficients, we put a little subscript I on the bottom, which now means that every individual I is going to have a different parameter, a different preference parameter, whatever it might be. So that gives you lots of flexibility, but obviously we don't have enough data to estimate the model by individual. So you make some assumption. You make an assumption that these parameters, the betas, are going to be distributed from some sort of distribution, usually or quite often a normal distribution, which has got a mean and a variance. So then when it comes to the estimation process, what you're doing is you're estimating the parameters of the distribution of your random parameters. So that gives you flexibility, but it's got some constraints because we're going to talk about distributions. So what does this look like? Well, here I've got my three parameters. They've got the means, the little b's are the mean of the distributions. They've all got the same variances because I was lazy. But for B1, let's say these are our first four people, person 1, 2, 3, 4. This is where they're scattered across the particular distribution. So person 4 has above average weight on that attribute. Person 1 has below average weight. Then there's a second parameter, same four people, 1, 2, 3, 4, and if I've done that right, those are going to be uncorrelated. You get no information about where somebody's preferences are for F2 from knowing something about what their preferences were for B1. So, yeah, you can see I've tried to rejig these so that, 4 used to be up at the top of the distribution, now it's come back down, but 3 has moved up slightly. Basically, there's no correlation between my preferences for F1 and F2. There's the coefficients for F3, and what you can hopefully see there is that those look as if they're quite strongly correlated. So if I was above average for B1, I tend to be above average for 3 and below average. They're not perfectly correlated, but there's just some sort of structure going on in the data. So this is what I'm going to be talking about a lot, is this idea of estimating random parameters, and it's the question about whether or not we're going to allow our random parameters to be correlated or not across the different parameters. So that's building block number 1. Building block number 2, categorical variables. So these are things which don't have a continuous scale to them. So if I'm asking somebody to choose a car they want to buy, green, blue, white. If we're going to include that in the model, we have to basically dummy code them. We just create a dummy D1, D2, D3 as to whether or not the car I'm looking at is green, blue, or white. And in estimation, you can only include n-1 dummies. So I've got a categorical variable with 3 levels. I can only include 2. because basically these always sum up to 1 for any particular choice set. The car has to be one of those 3 colours. So what that means is that whenever you drop one of these categories, as in I'm going to drop D1 and just have D2, D3 in the model, the parameters measure the value of a category relative to the base. So if we dropped D1, it's going to be what's the value of a blue car relative to a green one, what's the value of a white car relative to a green one. Doesn't matter which category you drop. So this is a standard thing when the first time you introduce this to students, and they ask you the question, well, which one do I drop? You say, it doesn't matter. The model doesn't change irrespective of which category you drop, in the sense that things like fit, Loglikelihoods, and so on are identical, and I can retrieve the parameters from any model from any other model. So it's just model invariance. I can drop D1, and I could predict what's going to happen if I were to drop D3. Okay, so that's the sort of the standard result. Doesn't matter which base. Okay, my bold statement at the start restated. When estimating models with categorical variables, these blue, green, white, the choice of the base category is going to influence your results, contrary to what we tell all our first-year students. If you use a random parameter framework, and if you use uncorrelated random parameters. So if you decide to estimate a model where you're going to say, I'm going to have these random parameters, but they're going to be uncorrelated to each other, and you're doing that with categorical variables, then the models you estimate depend upon which one you drop as base. So so the first statement's really bold, and then it gets qualified twice to something quite a little narrower, but it's still, I think, an interesting problem. Okay, what's the source of this problem? Why does this happen? So let's assume we've got this utility function for somebody. It's got 4 variables, x, which is going to be continuous. It's got these factor variables, categoricals, f1, f2, f3. They're distributed normally. And let's assume that in the data generating process, these are uncorrelated. So you can't predict anything about my preferences for green cars from information about white cars, my preferences for white cars. So at the data generating process, these parameters are uncorrelated. But when it comes to estimation, you have to drop one. You can't estimate a model with all 3 dummy variables in it. So we have to drop one of them. So what are we estimating at estimation stage? Well, we're estimating the relative values of f2, I've dropped f1, the relative value of f2 relative to f1. So if you just transform that and recognize that f1 is actually equal to 1 minus f2 minus f3, by definition they have to add up to 1, then essentially what you're estimating, this parameter, is a difference in marginal utilities between f2 and f1. Standard. Same here. But now you can see I've now got correlation. I started off without any correlation in the random parameters. I've now just induced it, because B1I, which is a random distribution, is turning up in both of these composites. So start off without any without any correlation in my random effects for these categorical variables. When I get to estimation, I've induced it. So there's almost bound to be some correlation happening across this sort of composite parameter that I'm estimating versus the one on F3. But if you insist on estimating your model using uncorrelated parameters, what are you implying? Well, there's 2 ways you can get it. The one is that the base category has got a constant marginal utility. So if this beta 1i actually isn't random, but it's a fixed coefficient, everybody has the same beta 1, then I don't induce any correlation, because this is just a constant across both of them. So there's this distributions are no longer correlated together. So you could claim that. Or you could say, well, by construction, the differences in marginal utility from the base are uncorrelated. So if I started off by saying, well, the data generating process is really this, beta 1 on F1, and beta 2 plus F1 on F2, and beta 3 plus beta 1 on F3. Now I play the trick, oh, I have to drop F1, make the differences, and, and the beta 1s disappear. So now I'm back to uncorrelated betas in the estimation. So you could ex post rationalize why you've used uncorrelated random parameters by saying either, well, the beta 1 is fixed, or by construction, the differences in margin utility are uncorrelated. But you can only play that game once. You can only play that game by saying, oh, well, beta 1 is constant, and therefore I can do the difference. But if I'd come through and said, oh, I'm going to drop F3, and use that as the base, then I still end up back with correlated random effects again. So the only way that I could make this justification, if I were to drop F3 and say they're uncorrelated, is by saying, well, the parameter on F3 is fixed. So every time I make drop a base out of the model, I'm essentially estimating a different model, a set of assumptions about preferences, if I insist on using uncorrelated random parameters.
So what you're saying is, whatever the base, it's always your assumption that that has a constant margin.
Yes. That would be a justification for doing it.
Yeah.
And obviously, you can't keep on doing that each time and saying, oh, well, now I'm going to estimate a different base. If you select a different category for the base, you're estimating a different model of preferences, basically. So let's do a little simulation. So I've simulated some data, got 1,000 respondents, invented respondents sitting in my computer. They each make 10 choices. They make the choices over 2 alternatives. The utility function that drives the choices depends upon a continuous variable x and 3 categorical variables. Put a random error term on the end so that we get a bit of randomness in their choices. It's not perfect. We're going to have to assume something about the distributions for these betas, because I'm going to simulate people's utility. I'm going to before we start this, we just draw 10,000 observations for the betas, which are going to drive the simulation. And we're going to make some assumptions about the parameters. So this is the mean, and that's the standard deviation of the distribution. Beta x is going to be 1. Beta 1 is going to be 1. Both of those are actually going to be constants. They're going to be fixed parameters. Beta 2 is 2 for the mean, 2, and then 3. And then the standard deviations going 2 and 3 as well. So I can get a simulated data set. I know what the true data generating process is because I've created it. And now we can see what happens if we estimate a different base for f. So, starting point. Ignore all the stuff about random parameters. Just estimate a bog standard model with fixed coefficients. So I've got x, I've got f1, f2, f3 as the variables. I have to drop one of them each time, so I'm going to estimate this model 3 times, dropping f1, dropping f2, dropping f3. And what you can see along the bottom is the log likelihood, and exactly the same. So this is the standard result that we tell to students. It doesn't matter which base you drop, because the models are basically invariant to which one I drop. And the x coefficient is identical, and you get this nice symmetry result, which is that if you've dropped f1, this is measuring the value of f2 relative to f1, plus 0.517. If I drop f2, this coefficient is measuring the value of f1 relative to f2. It's just the reverse. It's beautifully exactly the same number, but just negative. So numerically, absolute value is the same, it just changes the sign. Does exactly what you'd, and it's perfect symmetry. Exactly what you would hope to do. There's no invariance in this model. Re-estimate the model, but now using uncorrelated random parameters. Each time now we're going through, we're going to do model 1, model 2, model 3. We're going to drop which one we're going to use as a base. And instantly you can see the log likelihoods are not the same. all I've done is this really arbitrary, innocent little thing. I've changed which one I want to use as the base. Different to different to different. So these models are basically different representations of the preferences. And the symmetry issue has disappeared. If I use model 2 as the base and look at F3, so this is the value of F3 relative to F2, 1.038. Use F3 as the base, we are no longer equal and opposite, same value, opposite sign. It's not surprising because they're different models. They're different models of preferences that we're estimating. So this is the manifestation of the problem. If you do it properly and estimate this using correlated random parameters, so we can explicitly tell the estimation process, we're going to have a random parameter for F2, a random parameter F3, but now we're going to allow there to be a covariance between them. So that actually we're going to explicitly say you're allowed to correlate these parameters. Then, well, to within the degree of accuracy you'd expect from the estimation, because it's done by simulation. So I'm at what? First decimal point, 5756.6, 0.8, 0.65. So those are close enough to be saying actually we have the same models. And the parameters themselves are really very close. We're back to symmetry. 0.83 minus 0.83. That one's off at the third decimal place. But essentially, up to the accuracy you'd expect by estimating by simulation.
Rounding error, that was the same in the first table.
I thought...
No, the first, the very first.
Oh, okay, first. Yeah. So it's getting to the... Oh, I think I thought I went and re-estimate that. It's basically we don't... Those very small changes, and these very small changes in the log likelihood aren't an indication of a problem in the model. It's just the way we're estimating by simulation.
How much covariance do you need?
In what sense?
Well, between these parameters, it's a black and white, or is it a gray thing?
Well, what you can see is that well, who knows? What do you mean by how? There is no covariance on this estimate because we've dropped F1, and F1 was a fixed parameter, so that is not significant, which is good. It's what we'd predict. So that, in some sense, is the baseline log likelihood. What is an appropriate? I don't know. I'm not sure you can. Well, you'll see something in a minute that might answer the question. Who knows? That's an empirical question, Steve. Needs some degree. Okay, that might just be a really lucky draw of me. I've just generated 1,000 individuals, done one draw of the data, and shown you some results. An appropriate response would be, yeah, that you're just lucky. You've just shown us the results which confirm the story. Okay, rinse and repeat 500 times. So what we're going to do is draw that same sample of 1,000 people doing 10 choices with 2 observations. Each time we draw that sample, we're going to take the ratio of the estimated parameter to its true parameter. And we're going to report them here as ratios. So what we want, so if this has got a value of 1, it means that on average, over 500 draws, the ratio of the actual estimated parameter to the true one, on average, came out at 1, which suggests that we're actually, on average, getting pretty damn close to the true parameter.
So what's in this column?
The value in the brackets is the number of times that we rejected the hypothesis that the true parameter was equal to the estimated parameter. So this is basically a type 1 error proportion. So in 5.6% of the times, out of the 500, it's coming back and saying, actually, the estimated coefficient is statistically different from the true value, which I know what it is because I generated the data. So this first column looks beautiful. These are all really close to 1, and these are close enough to 5%, because that's what the alpha is, that you'd expect to see. So that all looks good.
Is it 5% or is it 5.6 times out of the
No, it's 5.6%. It's percentage, yeah.
And that's your correlated model.
And this, because there's a little footnote on it, is the correlated model. So that all looks beautiful. This is the uncorrelated model. So it's pretty good for the x. But we are suppressing the parameter estimate. So this is like 89%. On average, we're sort of 90% for F1, but we're down to 66 or 75. The type 1 error rate has gone up to 52, 84, 100%. So on the estimates of the variances, we are essentially every time would be rejecting the null that the estimated parameter equals the true parameter. So this is with, if you remember, the standard deviation for F3 was set at 3. Okay, let's just play. Let's set it at 4, 5, and 6 and do the whole game again. And you can just see that as this variance gets larger, standard deviation gets larger of the one that we're using as the base, as in it just gets worse, basically. Every time we get, the ratio gets further away from 1, the proportions that where we're rejecting the null. So systematically it's a problem. Okay, so this is me playing with data. Is it actually a problem out there in the real world? So I did a quick look through the health economics literature. So these are all what, 2006-17 papers. Value in Health, which is a big paper, a journal, PLOS One, Journal of Choice Modeling. These are all cases where their papers have been estimated using random parameters on categorical variables, and they're uncorrelated. So these are all papers that are published that have fallen into the trap that we've got here. And so essentially what we're saying is they'd have all reported different results if they'd chosen a different base level for their categorical variables. If they'd done something innocent, they would have, what we would think of as innocent, they'd have reported something different. So I wanted to actually test to see what happened on a published paper. I actually asked a couple of people for data sets, and they didn't want to share. For some reason, don't know why. PLOS One was good because they sometimes put the data sets up. They just load them up. Not all of them, but some of them do. So this paper actually put the data set up, so I can replicate it. What is it? It's about postnatal depression. Perinatal depression anxiety. Sorry, I should be more accurate in reading stuff. Discrete choice, so it's a health version. They've got lots of different types of treatment types for depression. So 8, individual counselling, group counselling, meditation, medication, all sorts of stuff. 8 of those, plus costs, plus a whole load of other different attributes. So this is about surveying women as to how they would like, what treatments they would most like. So that's a version of the choice set. You can have no treatment or 2 different treatments being offered, and this treatment type, group counselling, counselling medication, and there's a cost. So it just looks like a choice experiment, as a conventional one. I estimate a simplified model compared to their model. Only those treatment dummies, the 8 dummies, are going to be assumed to be random. They did all of them random. I'm not going to have any socio-demographic interactions with treatment, ASC. They had lots as to whether people opted in or out, but I wanted to make life simple. And I estimate it in willingness to pay space. But it's basically their data, so it's not really a complete replication of their paper, but it would show what would happen if you went through and estimated that model, dropping or using a different treatment method as the base. So you get all of this. So this has got 8 different models on here. These are the fixed coefficients. These are the means of the random distributions. And these are the standard deviations of the random parameters. So these are all estimated using uncorrelated random parameter models. And the difference is, you can see as you go down here, individual counselling, medication, and so on, what's being used as the base. That's a horrible table. Just look at the top row. That's the log likelihood. They vary. 2560, 2573, 2570, 61, 2585. So there's huge variations in the log likelihood just from changing the base. Just compare 2 of them. This is the ones where individual counselling and medication are used as the base. So we have the whole, individual counselling, medication. And the symmetry. The log likelihoods are different, what you expect. The symmetry's gone. So individual counselling relative to medication, minus 6873. Medication relative to individual, no, other way around. Medication relative to individual counselling, minus 0.6873. Individual counselling relative to medication, 6105. So this is the same comparison, just change the base of the model, and we're getting, what's that, over a 10%, 12% difference in the estimated parameter. Those are the standard deviations. An even bigger effect pops up here. When we use individual counselling as the baseline, then medication relative to individual counselling looks like there's a significant standard deviation. Apparently there's lots of individual heterogeneity in this population, as in some people have different values for medication relative to individual counselling compared to other people in the sample. Use medication as the baseline, it's gone away. Apparently, everybody views these two treatments the same in the sample. So one model says there's individual heterogeneity across our population. The other model says everybody's the same in terms of comparing these two treatments. Only difference in the models is we've changed the base. If you do this for the correlated models, everything goes back to being nice again. 2510.2, 2510.3, the log likelihoods have come back together again. Do I do that? No. There's 6591, 6638, so those have closed up again. The standard deviation significant and about the same size. So going to the correlated error, going to the correlated random parameter results gets us back to invariance again. It all works beautifully if you use correlated random parameters. They have a policy question, which is about if we had these different types of treatment in the market, who would take them up and what proportion? So what you can do is you can just do a simulation where you assume that all 8 treatments are available. They know what the costs are for the different 8 treatments in terms of they get an estimate as to what it costs for medication versus group counselling and so on. Just simulate what the market share would be across the treatments. So this lot add up to 100%. You can now just repeat that game for all 8 different models. And now the interesting thing is comparing across a row. So these are the predicted market shares as I change the base for the estimation. And there's some which really sort of start to pop. So this early parenting group support, it's 33.3% of the market if you use the group counselling as the base. It's 28.3% if you use early parenting as the base. So it's actually, is that a big number? Well, it's not at the decimal places. And there's another one down there. It goes from 14% to about 11%. So it's having implications as to what you might predict is happening in the market. Okay, examples in environmental and ag economics. That's a health one, so I presented this at the health conference, so that's why I did the health example first. Is there a similar problem out there in the environmental economics and ag economics literature? Again, a quick search over recent papers. So this is, okay, GEAM, Journal of Choice Modelling, GEAM, American Journal, all within the last 3 years, all having this same characteristic. They're going to estimate uncorrelated random parameter models using categorical variables. So these should also have the same problems. Couldn't get anybody find any data sets. So went and used this one. It's a deeply dodgy paper, which, possibly by accident, did it right. So this is a paper which is interested in the area of the allocation of land around wastewater treatment plants, and you can choose like what the composition is: nature conservation, commercial, agriculture, sporting and rec. And obviously these things add up to 100%. Is that right? Yes. If there's a problem in here, I've got a problem. And then just the options are, we're going to just change the proportions. See whether people would like to trade off and get more conservation versus, say, industry. So what's interesting about this is that these aren't categorical variables anymore. They're continuous variables. But they have the same characteristic. You have to drop one. I can't include all 4 variables in the estimation, because by definition they're up to 100, so they have this sort of correlation problem. So you have to drop one. And so this actually is going to have the same problem in terms of which base you drop, which one you use.
So it's not it's not the fact that they're categorical variables, it's the fact that they add up to 1 that really creates the
Yes,
problem, right?
yeah. The fact you have to drop one of them,
Yeah.
that's the important thing. In the original paper, I think possibly by chance, we used correlated random parameters, so we didn't fall into the trap. But the question is, what would have happened if we hadn't? What would have happened if we just estimated this model using uncorrelated random parameters? What would have been the consequences? So this is just an example of a real data set again. So this is doing it properly. So this is dropping the base each time. 1287, 1287, 1287, 1287. We're again, the differences are at the decimal point levels. The symmetry, the symmetry sort of is turning up. It's minus 264, 264, 1.52, minus 1.51. So we're within sort of, I'm comfortable that we're not, there's not a problem going on here. What would have happened if we'd done this with uncorrelated random parameters? So we're just going to estimate the same 4 models again, just go through and drop the base each time, to change the base each time. And, well, 1, the log likelihoods are all changing, 301, 305, 319, 1298. So it's making a big difference in terms of what we think is representation of the data. And the symmetry thing has been broken. So when we have commercial as the base, recreations plus 0.79, we'd rather have recreation than commercial. That's good. When we have recreation as the base, minus 1.07. Okay, the sign's gone right, as in we don't like commercial, but the size of it, those are supposed to be the same numbers in absolute value to represent the same preferences. That one's even more interesting. Recreation as the base, we don't want to see agricultural land in there compared to recreation significantly. But if I use agriculture as the base, apparently we're indifferent. It's a positive coefficient, but statistically it's saying, well, actually we don't really mind whether it's agriculture or recreation. So the policy implication has flipped as a result of that simple change. That's just the correlation. There is a variance-covariance structure, so that's why we're seeing the differences. What are the implications for willingness to pay? So that's what we're interested in this paper. So what do we do? Well, what you can do out of these models is you can generate, out of any model, for each individual an estimate of their willingness to pay. So what we can do is, if we take natural land use as the base, we can work out for each individual what their willingness to pay is for natural relative to commercial, and then work out what the mean is of all those numbers. So on average, across our sample, 300 and something people, I think, on average, they're willing to pay 250, but there's a distribution in there. Recreation, 0.58, agriculture, 0.32. So that's just, as everybody prefers these land uses to having commercial land use, that's fine. But then we can go through and just repeat the game. That's when we have natural as the base, commercial as the base, recreation and agriculture as the base. So just for those 4 different models, we're just going to change what the base is. These willingness to pay are always estimated natural relative to commercial. So what's interesting is, do these things change? And what you can do is there's a t-test, like an ANOVA test, but it's a test to see whether or not these distributions, the mean of these distributions is the same or not, and the reason it's not an ANOVA but a Hertelling is it takes advantage of the fact this is paired data. So I have got the same person giving me an estimate of this willingness to pay, and I can identify them in that model and that model. So this is like a generalization of the normal ANOVA test. It exploits the fact that I've got the same person giving me 4 repeated observations. Or each person in the sample is giving me 4 repeated observations. So then you hit it with the Hertelling t-squared test, and what pops out is, well, this recreation one is different. As in, it doesn't seem to actually influence. The choice of base, in terms of the average, isn't influencing the natural or the ag willingness to pay, but the recreation one it is, and you can sort of see it pops. There, it's about twice as large. So depending upon which model we had chosen, which base we had chosen, if you'd done it with uncorrelated random parameters, we could have either reported a willingness to pay for recreation of 58 cents per 1 percentage point, or 103. So that's, almost doubled it. And just not by doing anything fancy, just by changing the one we use as the base.
Just for clarification, so for the other attributes, there's no significant differences?
There are no other attributes in this model.
Oh, for the other levels?
For the other ones, yes. These are not significantly different from each other across the 3. The means of them are not different. So it's sort of just turning up in one of the willingness to pays.
So this is without correlation?
Without correlation, yeah. With correlation, it would be the same.
It's a bit like the pesky paper, where you simply don't know, you have to test whether it's going to be a problem or not.
Yeah. Or just estimate the proper model. I was about to see. Okay, so what you'd expect is that normally you'd say, okay, if you make a choice about model specification, it's going to change the results. That's just part of life. You choose a different model specification, it's going to have some impact on you. Typically, if you do that, you're going to be expected to justify your choices. You're going to have a reviewer saying, why have you decided to use a latent class model rather than a mixed logit or something? So we know it'll make a difference, but normally you're going to be held to account. You're going to be expected to justify the choice you made in terms of your model specification. You don't normally expect to have to justify which base you've chosen. That's usually a completely throwaway line in the paper saying, and we've chosen variable, level 1 as the base. And off you go. So that's usually a completely sort of, looks like an innocent thing that you just do and off you go and carry on next bit. But if you've got these uncorrelated random parameters, that choice is going to influence the results, possibly quite a lot. So model invariance seems to be a minimum expectation. So if you estimate models and you get different results, okay, model choice matters. But you'd have hoped that model invariance to arbitrary choices should just be a minimum expectation of your modeling strategy. Really, I shouldn't see any changes in the output I'm getting from my model as a result of making just this apparently innocent arbitrary, completely arbitrary. There's no theory which should tell you which one you should use the base. So, do that.
Unless it takes 4 days and then it's...
Do that even if it takes 4 days. Okay, so that's me done. Is that it? Yeah, thank you.